Welcome back to Very Ordinary Differential Equations. In this lecture, we return to the study of second-order Euler equations, but now with algebraic forcing functions. First, let's cover something known as the superposition principle, which sounds much fancier than it actually is. Suppose we're attempting to solve a second-order linear equation that's not homogeneous. But the forcing function f isn't just not zero, it's actually the sum of several other types of functions. For example, it's some f1 of x plus an f2 of x, etc. Well, what we know is, to find all solutions to the differential equation, we only need to find a fundamental set of solutions to the complementary homogeneous equation and one solution to the original. It might, however, be difficult to do this all at once, but maybe we can find particular solutions yp1, yp2, etc., so that if I use yp1, I get out exactly f1 of x. And if I use yp2, I get out exactly f2 of x. All the way, if I use ypk, I get out fk of x. So we're trying to solve a second-order linear equation that's not homogeneous, and the forcing function is actually a sum of many different pieces. But let's presume we have found various particular solutions if we just had one single piece at a time. So I have a particular solution yp1 that when I use it in the differential equation gives me this first part of the forcing function f1. And I have a solution yp2 that when used in the differential equation gives me f2 of x, and so forth. Now if I just set yp to be the sum of all of those things we've found, since differentiation is linear, overall the second derivative of yp is the sum of all of these second derivatives. The first derivative of yp is the sum of the first derivatives of all of these. And then I can distribute p of x and q of x and just collect all of my p1s and get out f1. Collect all of my p2 terms and get out f2, and so forth. So if I set yp to be the sum or superposition of all of these particular solutions, then it will actually solve the original inhomogeneous equation. So all we have to do is solve for each piece of the sum separately. And this is called the superposition principle. And it really just followed right from linearity of differentiation. So if your forcing function is a sum of various things, it can be extremely helpful to attack them one piece at a time and then create your particular solution by summing up the sort of partial solutions you found along the way. Well, let's discuss algebraic forcing functions. So let's go back to second order linear Euler equations, but with a forcing function which is algebraic, which just means a power of x. Okay, so let's start with a simple power function. Here's our second order Euler equation, x squared y prime plus something xy prime plus something y. And now we have a forcing function which is some constant times a power of x. Now earlier, what we observed is that letting y be x to the alpha led to a way to solve the complementary homogeneous equation. The same technique can be used to find the solution to this inhomogeneous equation. So here is our second order Euler equation with an algebraic forcing function. Let's presume that y is some constant times x to that same power. Okay, so whatever the power of the forcing function, I'm presuming my particular solution has the same power. Why am I doing that? Well, when I take one derivative, I'll get d times r times x to the r minus 1. And when I take two derivatives, we'll get dr r minus 1 times x to the r minus 2. But in our Euler equation, remember, you multiply by a power of x that exactly corresponds to how many derivatives you took. So x squared y double prime will exactly have x to the r. X y to the prime will exactly have x to the r. And y has an x to the r. So I can factor an x to the r out of the entire differential equation, meaning I can cancel it from both sides. And that will reduce to a d that can be factored out, so dr squared plus a minus 1r plus b must be the constant c. Therefore, d must be equal to c over r squared plus a minus 1r plus b. Notice we don't have to try to solve this for r, because the presumption is that r is the power on the forcing function. It's actually given in the problem. All we need to do is solve for this constant d, and here it is. So if we have an algebraic forcing function in our second order Euler equation, if I just set d to be c over r squared plus a minus 1r plus b, well then, y equals d times x to the r will be a particular solution. Now that denominator, r squared plus a minus 1r plus b, is exactly the characteristic equation that results when you make the relevant substitution, x equals e to the t, into the homogeneous Euler equation. So if x to the r happens to already be in the fundamental set of solutions, then that denominator will be 0 and this totally fails. However, if x to the r is not a solution to the homogeneous equation, well then that denominator won't be 0 and we're fine. So if x to the r is not in the fundamental set of solutions, if x to the r does not solve the homogeneous version of the equation we started with, then setting y equals d x to the r is a nice particular solution that we can use. But what if the forcing function actually is in the fundamental set of solutions? What if the forcing function solves the homogeneous equation? In other words, x to the r is our forcing function, but it also solves the second order Euler equation, x squared y double prime plus axy prime plus by equals 0. Well then, we have the same second order Euler equation with the same power of x as a forcing function. Now, similarly to finding solutions to the homogeneous complementary equation, what we'll do is we'll set y sub p to be x to the r times log x. If the homogeneous Euler equation had repeated x and therefore c x to the r log x was already in the fundamental set of solutions, then what we do is we use the same power of x but with log x squared. So let's take all of this theory and put it into practice by finding a single solution to x squared y double prime minus xy prime plus y equals 4x. The complementary equation has a fundamental set of solutions x and log x, because 1 is a repeated root of r squared minus 2r plus 1 equals 0. Remember, when dealing with Euler equations, this middle coefficient is going to be reduced by 1 when you create your complementary equation. So r squared minus 2r plus 1 has a repeated root of 1, so x and x log x form our fundamental set of solutions. However, the forcing function is x, which is in our fundamental set of solutions. So we would try x log x, but that's also in our fundamental set of solutions. So we try 4x log x squared over 2. This was the formula that was presented earlier. 2x log x squared. What we can do is now verify, here's the first derivative and the second derivative. Now if I take this first and second derivative, I multiply them by x and x squared respectively and throw them into the differential equation. X squared y double prime minus xy prime plus y is going to be 4x log x plus 4x minus 2x log x squared minus 4x log x plus 2x log x squared. And a lot of stuff cancels out, and what doesn't cancel out is exactly the 4x, in other words, our desired forcing function. So when your complementary equation has a repeated root, so you end up with x to a power and x to that power times log x as your fundamental set of solutions. When that's exactly the power you have as your forcing function, you have to take coefficient x log x squared over 2. 4x log x squared over 2. And here was our particular solution. As a second example, let's find all solutions to the equation x squared y double prime plus 2xy prime minus 2y equals root x minus 1 over x. First, let's find a fundamental set of solutions to the complementary equation. Well, that's a second order Euler equation, so we set a is 2 and b is minus 2 and compute the roots of r squared plus a minus 1r plus b. Remember, you got to subtract 1 from that middle coefficient when dealing with Euler equations. So that's just r squared plus r minus 2 equals 0. Factors very nicely as r plus 2 and r minus 1. So it has two roots, 1 and negative 2. So a fundamental set of solutions is given by x to the first and x to the minus second. Well, with our fundamental set of solutions to the complementary homogeneous equation behind us, we can turn our attention to finding a particular solution to generate our forcing function. The forcing function, however, is a sum of two different terms, a root x and minus 1 over x. So we're going to do this one bit at a time. First, we'll find a yp1, so that if I use it in the differential equation, it generates x to the 1/2, or root x. Then we're going to find a yp2, so that it would generate x to the -1, in other words, 1 over x. By the superposition principle, if I take yp1 minus yp2, that will generate x to the 1/2 minus 1 over x. Thankfully, neither of these powers were powers in the fundamental set of solutions, so we don't have to be too tricky here. So first up, let's try to produce a forcing function of root x. We presume that y is some power times root x. Then we know from all of our earlier work that all we have to do is solve for c to be 1 over r squared plus a minus 1r plus b. R is 1/2, it's the power on our forcing function. A is 2, it's the coefficient here, and b is -2, the coefficient there. So all we have to do is plug that in and compute the value of c. Works out to be c is -4/5, so we set yp1 is -4/5 times root x. Next, we just have to find a particular function so that when I use it in the differential equation, it will produce x to the -1, in other words, 1 over x. So I presume that y is some constant times 1 over x. From all the same work, all we've changed here is what the power is. The power is now just -1. So we compute c to be 1 over r squared plus a minus 1r plus b, which works out to be c is -1/2. So we set yp2 to be -1/2 times 1 over x. So by the superposition principle, all we have to do is set our particular solution to be the difference of the two we found. We're taking a difference here because there's a minus sign here. So we end up with -4/5 root x plus 1 over 2x. So now that will solve x squared times the second derivative of this plus 2x times its first derivative minus 2 times it will give me root x minus 1 over x. Remember that our fundamental set of solutions was x and x to the -2, so therefore all solutions are given by our particular solution plus linear combinations of this fundamental set. So -4 root x over 5 plus 1 over 2x plus some constant times x plus some constant over x squared. And there we have all solutions to the differential equation with this specific forcing function of root x minus 1 over x. Next, let's solve an initial value problem. X squared y double prime plus 5xy prime plus 4y equals pi x to the root 2, with initial values y of 1 is 0 and y prime of 1 is 0. First, we got to find a fundamental set of solutions to the complementary equation. Set A is 5, B is 4. Solve for r squared plus a minus 1r plus b equals 0. There's a single real root of 2. So a fundamental set of solutions is given by x squared and x squared log x. Now we have to find one solution to the original equation, y sub p. Now, unlike earlier examples we've worked through, our forcing function is not just being multiplied by 1, it's being multiplied by pi. This does in fact affect how we solve for the particular solution y sub p. So we might try to divide it out. If I divide everything by pi, we would end up with this expression right here. The good news is the forcing function doesn't have a pi in front of it. The bad news is everything else does, and in fact the leading coefficient, not being just x squared times y double prime, but having this 1 over pi, means it does not match our general format for a second order Euler equation. Also, all those denominators of pi is probably going to make the later work we do really unpleasant, so we don't want to do it this way. Rather, let's revisit how we solved for c. Specifically, we were going to let our particular solution be some constant times x to the root 2, and what we would find is that c times r squared plus a minus 1r plus b is 1. The 1 on the right, however, in the earlier work, just came out to be the coefficient of x to the r in the forcing function, so we don't really have to change very much. So in this particular problem, if we assume our particular solution is some constant times x to the root 2, we would end up solving for that constant times this characteristic polynomial equals pi. Not very difficult, just divide by that characteristic polynomial, and c must be pi over r squared plus a minus 1r plus b. In this particular problem, the power on the forcing function was root 2, the coefficient on our middle term was 5, and our coefficient on our last term was 4. So we end up with that constant c must be pi over 6 plus 4 root 2. In other words, our particular solution is given by pi over 6 plus 4 root 2 times x to the root 2. So we have found a particular solution, and we already found a fundamental set of solutions to the homogeneous complementary equation. So now we can state all possible solutions to this differential equation are given by the one particular solution we found plus linear combinations of elements of the fundamental set of solutions. Now we can start using our initial conditions. Let's take a look at y of 1 equals 0. Well, if y of 1 is 0, I just substitute 1 for x, and log of 1 is 0, so this term vanishes. Here I get c1 times 1. 1 to the root 2 is just 1. And if y of 1 is 0, my left is 0. This allows me to solve for c1 quite directly. There it is. c1 must be negative pi over 6 plus 4 root 2. So we have found our general solution. It must be our particular solution plus a linear combination of our fundamental set of solutions to the complementary homogeneous equation. And now let's take y prime. Well, taking one derivative of this is not the most fun we've ever had, but it's not so bad, and we end up with this expression right here. And also, y prime of 1 is 0. So we take that information, we plug it in. We get 0 must be y prime of 1, and by substituting a 1 for all of our x's, we end up with this expression right there. Now, c2 is now expressed in terms of c1, okay? But we already found a value for c1. So with c2 being equal to this expression right here, and we already found that c1 is negative pi over 6 plus 4 root 2, well, overall, this gives that c2 must be positive 3 pi over 2 times 6 plus 4 root 2. And now we can finally state our solution. We had that our general solution was the particular solution plus some linear combination of our fundamental set of solutions, and we have solved for c1 and c2, so we plug those in. Here is the solution to this differential equation with those initial values. Altogether, what have we done? The superposition principle, it's a very general thing. It says, if you want to find a particular solution to an inhomogeneous equation, and the forcing function is a sum of various parts, just find solutions to generate one part at a time, and then add those bits back together. And in the very specific situation where we had second-order Euler equations, and the forcing function was just a power of x, where that power of x does not solve the complementary homogeneous second-order Euler equation, then any particular solution can be found as some multiple of that specific power of x, and then you just solve for d. However, when that power of x of the forcing function does solve the complementary equation, try using some multiple of that power of x times a log of x, or times log x squared over 2, if x to the alpha log x is also a solution to the complementary equation. If the forcing function is a sum of various powers, the superposition principle, as stated above, can come in to help us.